The name of this module is UMPU test for multiparameter exponential family 2. In the last module, we have seen that if the power function of a UMP test is, if a power function of a test which is UMP among the all alpha similar test is continuous, then it is UMPU of level alpha. In this module, we use this result to derive UMPU test for multiparameter exponential family. First, we shall derive some conditional tests given some statistic t upper 2, and then we show that the test will provide UMPU test. Some examples are discussed in this connection. We use the ancillary statistic and we use Bosco's theorem to simplify the cutoff points of the conditional test. In the last module, we have shown that if power function of every test is continuous, then UMP test phi naught within the class of all alpha similar test is UMPU at level alpha. For testing h colon theta belongs to script theta h versus HA theta belongs to script theta HA. In the present module, we are going to explore this idea for constructing UMPU test when the distribution of x belonging to the k parameter exponential family. Suppose the PMF or PDF of x is of the form p theta x equals to some a theta into exponential summation I from 1 to k theta I ti into hx, where theta is vector valued with k elements theta 1, theta 2, theta k. We write it as theta 1 comma theta upper 2, where theta upper 2 indicates the remaining parameters theta 2 up to theta k. Let capital T equals to T1, T2, Tk is a statistic, vector value statistic. We write it as T1 comma T upper 2. Since we are dealing with multiparameter exponential family, we can consider the following set of assumptions. Number 1, power function of any test phi is continuous. Number 2, del to the power m by del theta to the power n integral phi p theta x d mu is equals to integral phi del to the power m by del theta to the power m p theta x d mu. That is, we can interchange and differential sign over the integral sign. Number 3, conditional distribution of T1 given T upper 2 is of the form one parameter exponential family. This is the same form as before. And the fourth assumption is T upper 2 is complete sufficient for PBT provided script theta b contains a k minus 1 dimensional rectangle. First, we consider the problem of testing h colon theta 1 less than equal to theta 1 naught versus h a colon theta 1 greater than theta 1 naught. Since the conditional distribution of T1 given T upper 2 belonging to one parameter exponential family, so it possesses the MLR property. Then by Carlin-Rubin theorem, as it was discussed earlier, the UMP test for testing h colon theta 1 equals to theta 1 naught versus h a colon theta 1 greater than theta 1 naught at level alpha based on the conditional distribution of T1 given T upper 2 is given by phi naught T1 comma T upper 2 is equals to 1 if T1 greater than some constant C, it depends on T upper 2, equal to gamma, which may depends on T upper 2 if T1 equal to C, and is equals to 0 if T1 less than C, where C and gamma are such that expectation under theta 1 naught phi naught T1 T2 given T upper 2 is equals to alpha almost everywhere on PB T upper 2. Now we have show that number 1, phi naught is UMP within the class of all alpha similar tests on script theta b, and number 2, phi naught is a level alpha test for testing H colon theta 1 less than equal to theta 1 naught versus H a theta 1 greater than theta 1 naught. Let us define CNS equal to set of all phi such that expectation of phi given T2 is equals to alpha almost everywhere on script PB T2. We also define CS, this is the set of all alpha similar tests on script theta b, and the previous class is the set of all tests having name and structure with respect to T upper 2. We also define CU, this is the class of all unbiased tests. This is the class of all test phi such that E theta phi less than equal to alpha for all theta belongs to script theta h, and E theta phi greater than equal to alpha for all theta belongs to script theta h a. Now phi naught belongs to CNS and hence phi naught belongs to CS, because we know that if a test have a name and structure then it must be alpha similar. Let phi be any alpha similar test on script theta b, since T upper 2 is boundedly complete, actually complete for script theta b, then our result 4 of our previous module, then any alpha similar test has a name and structure. So expectation of psi given T upper 2 is equals to alpha almost everywhere on script PB T2, because phi naught is UMP within CNS. Expectation under theta phi naught is equals to expectation under theta upper 2 within bracket expectation under theta 1 phi naught given T upper 2, and this is greater than equals to expectation under theta upper 2 expectation theta 1 psi given T upper 2, and this is equals to expectation under theta phi for all theta belongs to script theta h a. So phi naught is UMP within the class of all alpha similar tests CS. To prove 1, it is to be noted that expectation under theta 1 phi naught given T upper 2 is increasing in theta 1. This imply expectation under theta 1 phi naught given T upper 2 is less than equals to expectation under theta 1 naught phi naught given T upper 2, which is equal to alpha for all theta 1 less than equal to theta 1 naught. This imply expectation of phi naught under theta is equals to expectation of theta 1 under theta 1 phi naught given T upper 2, which is less than equal to alpha for all theta belongs to script theta h. This imply phi naught belongs to CU. Therefore phi naught is UMPU of level alpha. We consider some examples. Let x1, x2, xn be a random sample of size n from normal mu sigma square population where mu and sigma are both unknown. We consider the following hypothesis: h1 colon mu less than equals to 0 versus h1 a mu greater than 0. Now the joint PDF of x1, x2, xn can be written in the form of an one parameter exponential family. This is the form of c theta 1 theta apart 2 into exponential t1 theta 1 t1 plus theta apart 2 t apart 2 into hx by proper choice of theta 1 t1 theta 2 etc. Hence h1 can be written as h1 colon theta 1 equal to 0, then script theta b equals to set of all theta 1 comma theta apart 2 with theta 1 equal to 0. Note that t1 comma t apart 2 are jointly sufficient for theta 1 comma theta apart 2. Then t is sufficient for script theta b, which is also complete and hence boundedly complete. Thus the test is given by psi t1 comma t apart 2 is equal to 1 if t1 greater than equals to c, c depends on t apart 2 equal to 0 if t1 less than c, with expectation of psi given t apart 2 is equals to alpha almost everywhere PBT2 is uniformly most powerful UMP alpha similar test. Now we define V. V is a function of t1 and t apart 2. This is equal to t1 by t apart 2 minus n theta 1 square. It is increasing in t1 given t apart 2. Note that V t1 t apart 2 is equals to actually x bar by root over summation xi minus x bar square, and it follows t distribution with n minus 1 degrees of freedom under script theta b. Therefore, probability under theta 1 equal to 0, t1 greater than c t2 given t apart 2 is actually probability theta 1 equal to 0 v t1 t2 given v t1 t2 greater than c t2 given t apart 2, and it is actually probability theta 1 equal to under theta 1 0 v into root over n into n minus 1 greater than t alpha n minus 1. This is equals to alpha. Hence the test phi t1 t2 equals to 1 if root n x bar by s greater than t alpha n minus 1 equal to 0 if root n x bar by s less than equal to t alpha n minus 1 is UMPU psi alpha test. In the above example, we see that to evaluate the cutoff points of this test, we need the conditional distribution of t1 given t apart 2, which may not be easy to obtain in all the cases, and also it may be difficult to work with them. So it will be better if we choose conditional tests can be converted into unconditional tests by some means, and it is possible to do so if there exists a suitable function v. V is a function of t1 and t apart 2 of the sufficient statistics t1 t apart 2 which is independent of t apart 2. Our aim is to find a statistic v such that v is strictly increasing function of t1 for fixed t apart 2 and v and t apart 2 are independent. Then the conditional base test is given by phi naught v t apart 2 is equals to 1 if v greater than some v of t apart 2 equal to gamma if it is equals to, and it is equals to 0 if v less than some v t apart 2, where v of t apart 2 and gamma are such that expectation under theta 1 naught phi naught is given t apart 2 is equals to alpha. Since v and t apart 2 are independently distributed, the UMPU test is given by phi naught v equal to 1 if v greater than v naught equal to gamma if v equal to v naught equal to 0 if v less than v naught, where v naught and gamma are such that expectation of phi naught under theta 1 naught is equals to alpha. Now we discuss a choice of v. The statistic v can be obtained by using the concept of ancillarity. which has been already discussed in module 12. We know that a statistic V is ancillary for a family script P or for theta star if the distribution of V is independent of any P belongs to script P or for any theta belongs to script theta star. We have also discussed Bosco's theorem in this context. Suppose T is boundedly complete for script theta star and V is ancillary for script theta star, then for V and T are independent, then V and T are independent on script theta star. In the last example, the distribution of V T1 T apart 2 is independent of script theta B and T apart 2 is complete sufficient for script theta B. So V T1 T apart 2 and T apart 2 are independent. We consider our second example. Let x1, x2, xn be a random sample of size n from normal mu sigma square population where mu or sigma square are both unknown. We consider the following hypothesis: H2 sigma square less than equal to sigma square naught versus H2a sigma square greater than sigma square naught. Similarly, in this case we can rewrite the joint PDF as in a form of a one parameter exponential family. This is the form: C is a function of theta 1 theta apart 2 e to the power t1 theta 1 plus theta apart 2 t2 plus hx, where theta 1 and theta apart 2 are given, and t1 is equals to summation xi square and t2 is equals to summation xi. Here script theta b equal to set of all theta 1 theta apart 2 with theta 1 equal to 0, and H2 implies is equivalent to H2 theta 1 less than equals to 0, where H2 and whereas H2a is equivalent to theta 1 greater than 0. UMP alpha similar test is given by psi t1 t apart 2 equal to 1 if t1 greater than some c of is a function of t apart 2 equal to 0 if t1 less than c, with expectation under theta 1 equal to 0 phi t1 t2 is equals to alpha under theta 1 equal to 0, that is sigma square equal to sigma naught square, and t equal to summation xi is sufficient for theta, it is also complete. Here the corresponding ancillary statistic is V equal to summation xi minus x bar square. When theta 1 equal to 0, xi minus x bar are all identically distributed and are independent of all nuisance parameter. By Bosco's theorem, V and T are independently distributed whenever theta 1 equal to 0. Now we define V equal to summation xi minus x bar square is equals to t1 minus t apart 2 by n. It is increasing in t1 for given t apart 2, which follows sigma square chi square by n minus 1. Hence, phi t1 t apart 2 is of the form 1 if n minus 1 into s square by sigma naught square greater than chi square alpha n minus 1 equal to 0 if n minus 1 s square by sigma naught square less than equal to chi square alpha n minus 1. Now we consider our third example. Let x1 follows binomial n1 comma theta 1 and x2 follows binomial n2 comma theta 2 independently. Consider the following testing problem for the hypothesis h colon theta 1 equals to theta 2 versus h a colon theta 1 greater than theta 2. Now the joint PMF of x1 and x2 is given by n1 choose x1 into n2 choose x2 theta 1 to the power x1 into 1 minus theta 1 to the power n1 minus x1 into theta 2 to the power x2 into 1 minus theta 2 to the power n2 minus x2, and under the null hypothesis, if we take both theta 1 and theta 2 are equal to theta, this is of the form in the exponential family, just n1 c1 n2 choose x2 exponential x1 into some tau plus x1 plus x2 theta. Actually theta is the log odds ratio. Theta actually the log of theta 2 by 1 minus theta 2, and tau is equal to the log of theta 1 by 1 minus theta 1 minus log of theta 2 by 1 minus theta 2 is the log odds ratio. Now we define Sx equals to x1 and Tx equals to x1 plus x2, and UMP test of level alpha is given by psi s t equal to 1 if a is greater than some c, it's the function of t equal to alpha equal to gamma, if a is equal to ct equal to 0 if a is less than ct, where ct and at are such that expectation of psi under tau equal to 0 is equals to alpha for all t. Under tau equal to 0, s given t equal to small t has the following PMF: probability s equal to s given t equal to n1 cs n2 choose t minus s by n1 plus n2 choose t. This is the form of a hypergeometric distribution. In the last lecture, we have considered 3 examples. In the first example, we considered the test of mu less than equals to 0 against mu greater than 0 in normal mu sigma square population, and we see that the UMPU test is based on the statistic root n x bar by s, which follows Tn minus 1 under h naught. In the second example, we considered the problem of testing sigma square less than equal to sigma square naught versus sigma square greater than sigma square naught in normal mu sigma square population. Here we see that the UMPU test is based on the statistic n minus 1 s square by sigma naught square, which follows chi-square distribution n minus 1 degrees of freedom. In the third example, we have considered the test for theta 1 equal to theta 2 against theta 1 greater than theta 2 in 2 binomial populations with parameters n1 theta 1 and n2 theta 2. Here we see that the conditional test is given by the conditional distribution of x1 given x1 plus x2, and under h naught it follows a hypergeometric distribution.